Now, I've made a few videos in the past trying to shed some light on cell and battery performance, and some of those are on the screen right now. But in this video I'm going to share with you some information about internal resistance, and I'll show you how to measure it in a cell or battery. But first, what is internal resistance, and why would you care about it or even want to measure it? Well, your cell stores energy, but it also contains materials through which the electrons must flow in order to release this energy, in order to give you that voltage and current. These materials will have their own combined resistance, and a cell consists of not just energy but a built-in resistor. So that's what internal resistance is. Now, why would you want to measure it? Well, you may have noticed that some of the higher capacity 18650 cells have lower current drain limits. This is the NCR 18650B. It's a C2 cell. The highest capacity 18650 right now is the Panasonic NCR 18650G at 3600 milliamp hours. But again, you can only drain it at C2, which is 2 times 3600 or 7.2 amps. Now, some of our friends in the extreme vaping community are on the quest for the cumulonimbus of vaping clouds and prefer high drain devices such as the LG HG2. It's a C6 cell, capacity a little bit lower, although indeed this is on the high end of the high drain cells for capacity, and it can drain at 6 times 3000 milliamps, or a whopping 18 amps continuous, and even higher at burst currents. The cell has a lower internal resistance than the Panasonic, which has a high internal resistance. So that's the natural internal resistance, and you live with it either because you want a high capacity cell or a high drain cell. So after making your choice, why would you want to continue to measure it? Well, as your cell is recycled, unfortunately we get an unwanted or a parasitic chemical reaction between the anode, the lithium ions, and the electrolyte, which forms a coating, a solid layer on the anode. And as it builds up, it prevents the free movement of ions in the cell. And guess what? As it builds up, the internal resistance increases. So it's a very good indicator of the internal health of your cell. Now, the layer is called the solid electrolyte interface, and some chaps at the US Department of Energy's Oak Ridge lab have a TEM to play with, and they've captured an image of the buildup of the SEI on the anode. And that's what's happening right now in your lithium-ion cells as they go through the charge and discharge process. Now, a common additive used in pretty much all electrolytes by all manufacturers to prevent this build-up is vinylene carbonate. Now, it does help, but it doesn't prevent the SEI from forming. And I'll share a tip with you at the end of the video, how you can help the vinylene carbonate extend the life of the cells as you charge and discharge them. But aside from checking the available discharge capacity by completely discharging your cell through a meter, internal resistance is probably the next best indicator you can use to determine the internal health of your cell with a transient measurement. So that's why you might feel inclined to measure it. Firstly, when you get a new cell, and then from time to time to check its continued health. Now, there are chargers that will check the internal resistance. I've got a couple that do that, the Sky RCB6 and the MC3000, but perhaps you don't. Unfortunately, my battery Bible doesn't say much about internal resistance. It's got one page on it. So what I'll do now is take you through the manual measurement of internal resistance of a cell, and to do that we're going to need a few things. And yes, you guessed it, it's a Commodore Garden voltmeter, and we're going to need a resistor. But we're also going to need a couple of German laws. We're going to need Ohm's law and Kirchhoff's voltage law. Now, you remember your old school science experiments? What was it? Method, results, conclusion, or probably health and safety in there today, no doubt. The method we're going to use is we're going to measure the open voltage on a cell. We're going to measure the voltage on the cell with a resistor attached to it. Then we're going to use Ohm's law to determine the current. We're going to use Kirchhoff's law to determine the voltage drop on the internal resistance, and then we're going to use Ohm's law again to determine the internal resistance on the cell. Now, that sounds quite daunting, I suppose, to some people, but honestly, it's dead easy. Just a couple of measurements and you'll be sorted. So let's get cracking. We'll start with the LG HG2. Now, it does help if you've got something to put these cells in to measure them, preferably a 4-wire connector, but it's not necessary. And first step is to measure the open voltage on the cell. So I'll just get the probes on there. And what have we got? We've got 4.1 volts. I'll call that V open, 4.10 volts, V open. Next thing we do is we pop the resistor across and check the voltage drop. I just let it settle down for a while, not too long because you're draining your battery and it'll always change, but 4.04. I'll call that VR. And guess what? That's the data collection over with. I told you it wasn't going to be difficult. Right, just pop those over there, get rid of this, clear the desk. So, V equals IR. Now, with the resistor in place, we had a voltage of 4.04. So 4.04 volts, and we take the resistance down, and I used a 1 ohm resistor. Now, you can use any resistor you want, just make sure that the power rating is correct. I use 1 ohm to keep the maths simple. It's a 20 watt resistor. So divided by 1 equals, handily, 4.04 amps. So now we've got the amps flowing through the circuit. But according to Kirchhoff's laws, we've lost a few volts on the way. Well, not volts, but we've lost some potential difference. Kirchhoff's laws say that the complete set of voltages in both directions should equal 0. Now, we have 4.1 on the open circuit cell, and we've lost 0.06. So 4.10 take away 4.04 means the voltage drop due to the internal resistance on the cell is 0.06 volts. There we go. So now we've got the current, we've got the voltage, and what we can do is we can take voltage over current equals resistance, and the voltage is 0.06. that's the voltage drop attributable to the internal resistance, divided by 4.04. and where's my calculator? 0.06 divided by 4.04. You can see that's 0.01485. Let's call it 15 milliohms. And that is the internal resistance of this cell. Now, if you've stuck with me, let me just share with you the tip for extending the life of your lithium-ion cells. Now, the SEI, the solid electrical interface, enjoys high voltages. It thrives on them. So if you just back off your cut-off voltage on charge by 0.1 of a volt, from 4.2 to 4.1, you can extend the life cycle coefficient of your cells considerably. The electrolyte is always a trade-off between capacity, current drain and SEI build-up, and high capacity cells in particular can benefit from just less than a full charge to extend their life cycles. One final point, if you are going to measure your cells to check the health of them, make sure you do it at the same voltage each time, preferably at nominal voltage or at fully charged, which remember now is 4.1, not 4.2. Don't go measuring it at different voltages, because the resistance does change as the cell naturally charges and discharges. So get an apples to apples comparison, do it at nominal or do it at full charge. I hope this has helped, and if it did, I'll be grateful for a thumbs up. Cheers!